So now we have just a quick result on multiplicities. So the multiplicity of an eigenvalue lambda is the dimension of the generalized eigenspace. And since we've seen that the generalized eigenspace is the null space of t minus lambda I to a power big enough to kill it off, because it's going to be nilpotent, and we saw that the dimension of v will always do that. So we can take the formula to be this. Okay, so just quick side note. In many texts, this is called the algebraic multiplicity. Algebraic multiplicity in contrast to geometric multiplicity. So it's called algebraic multiplicity because it coincides with the multiplicity of lambda as a root of a polynomial. And it's a polynomial called the characteristic polynomial. And we'll define this in the next chapter. You've seen one definition of this already in your previous linear algebra course as the determinant of t minus lambda I. Now, of course, in this book, Axler hates determinants, so he's not going to define it that way. He's going to define it a different, equivalent way. But you still have some idea, I should hope, of what the characteristic polynomial is. And so, as I also remarked, this is in contrast to the geometric multiplicity. And the geometric multiplicity is the dimension of the corresponding eigenspace. Okay, so it's the dimension of the generalized eigenspace versus the dimension of the eigenspace. And so in the case when the dimension of the eigenspace is strictly less than the dimension of the generalized eigenspace, or in other words, when the geometric multiplicity is strictly less than the algebraic multiplicity, we say that the matrix is defective. Not a nice word. Anyways, so that's a little bit of, I don't know, mathematical bias, I guess, against generalized eigenvectors. Anyway, so that's just to tie it to what you already know. We won't really use the terms algebraic multiplicity and geometric multiplicity. For us, multiplicity will just be this guy, the dimension of the generalized eigenspace. Okay, so quick result about this, and that is that if we're dealing with a complex vector space and a linear operator on it, then the sum of the multiplicities of the eigenvalues, and we sum over all eigenvalues, so we're summing over the spectrum of T, is the dimension of V. Okay, so for the proof of this proposition, theorem 821 gives us that V has a direct sum decomposition in terms of the generalized eigenspaces, right? And then this implies, since it's a direct sum, that the dimension of V is the sum of the dimensions of G lambda k's. And so that's by 378, which says that it's a direct sum if and only if you have this equation for the corresponding dimensions. And then this is by definition the sum of the multiplicities of the lambdas. And that's by definition of multiplicity. And that's it, the end. Short and sweet. You get a box.